Right, here we are on page 4 of the study guide of Unit 1 review. And so we're going to draw the graph of the area bounded by these inequalities. So first, when I go to start graphing, I'm going to do this one in pink. So this is a y is less than or equal to 2x plus 5. So we begin at plus 5, and from there our slope goes up 2 over 1, up 2 over 1, or down 2 back 1. And then let's connect that with a straight line. Now, this is a solid line because y is less than or equal. Since it has the solid line, it includes all the point values on that line. So our solid line is now going to have shading of less than or everything underneath that graph. All right, let's go do the next one. Next one begins at positive 10. And graph is down 3 over 1, down 3 over 1. And this one's going to be a dashed line because it has a less than or equal to, it does not have an or equal to. So began at 10, went down 3 over 1. It is dashed because it's just less than. So just less than this graph means we're going to shade everything underneath that dashed line. Finally, this one right here, I prefer to look at it the other way around by rewriting it as y is greater than or equal to 0. I'm just flipping that one around so I can see it better. All right, so this one's going to be a solid line, and it's just a horizontal line through 0. So I'm going to go ahead and just draw a nice solid line through y equals 0. And this one's shading greater than or equal. So everything above this line. So where do I have pink and green and blue shaded? That would be this little triangular region here in between them all. So here I go darkly shading my region that is a solution to all 3 of these inequalities. Now remember that the pink line was solid, it includes those values. The blue line was solid, it includes those values. The green line was not solid, it does not include those values. So draw the graph of the area bounded. This is my solution. So the shaded feasible region is the solution to this system of inequalities. The darkest shaded region represents overlap of all 3. If I were to ask you what is one solution of this inequality, you would have to pick a dot that's within this region. So for example, 0, 2 is within this region. If I plugged in 0, 2 to any of these, it would give us a true statement. Choosing one dot within the shaded region would be a correct solution. The first term of an arithmetic sequence is 2, and the fourth term is 11. Write the explicit and recursive functions for this sequence. So the first term of a sequence is 2. We write that as 1, 2. The fourth term is 11. We write that as 4, 11. So first I need to calculate the slope. So m equals y minus y, or 11 minus 2, over 4 minus 1, so that gives us 9 over 3, or a slope of reduced just down to 3. So now that I have the slope and I have a point, I can write the explicit using point-slope form. Y minus 2 equals 3x minus 1. That's one right answer. Second right answer would be if you used the other coordinate pair. Y minus 11 equals 3x minus 4. You could also write this in slope-intercept form as 3x. Now check this out. If I distribute it, 3x minus 3, add 2, it would just be a minus 1. Some students might be able to look at this and see that if I subtracted 3 and went back to a step 0, that it would be minus 1. All of these are explicit forms of this equation. Now, if you recall from Math 1, we might have written it as the sequence begins with 2, is adding 3 every time to the x minus 1. Well, guess what? If I move this around, it looks just like this one up here, our explicit function. All of these are explicit functions. You can write them in point-slope form. You can write them in slope-intercept form. These are all considered the explicit. To write the recursive, there's two parts. We write f of 1 equals 2. That tells us that the first term in the sequence is 2. And then f of n equals f of n minus 1, adding 3 each time. And there's my recursive. For the following questions, use the system of equations. Solve the system of equations using substitution or elimination method, and then verify your solution by graphing these two. So notice that it's 3x and 2x, and it's 2y and negative 4y. There are no opposites already made. So in the top row, if I multiplied it the entire row by 2, I would be able to get a whole new row that did make opposites. So here I go. 2 times 3x gives me 6x. 2 times 2y gives me 4y. And 2 times 14 equals 28. Here's my new top row equation. Bottom row can stay the same because I already have opposites. 2x minus 4y equals 4. Now I can perform the elimination or the linear combination by crossing this guy out. And 6x plus 2x equals 8x. And 28 plus 4 equals 32. Divide by 8, divide by 8, I get that x equals 4. All that work for half an answer. I now need to plug back into either any of the three equations. So I'm going to go use the original 3x. Plugging in x is 4 plus 2y equals 14. Subtract 12 from both sides. Get that 2y equals 2. Divide by 2, divide by 2, get that y equals 1. So my solution to the system is 4, 1, and that's the point of intersection. So let's go graph these and see if it shows it touching at 4, 1. Now this over here is not quite ready to graph if you're used to graphing from slope-intercept form. I have to subtract the 3x's from both sides. So negative 3x plus 14. Then I need to divide everything by 2. That's going to give me negative 3 halves x plus 7 after I divide everything by 2. Now this is ready to go graph. Begins at 7, down 3 over 2, down 3 over 2. And here's my first line. Let's go do the second one. I'm going to subtract the 2 x's from both sides. I'm going to get negative 2x plus 4. And I divide by negative 4y to both sides. Remember that negative divided by negative is going to give me positive 2/4, which I can reduce down to a positive 1/2, leaving me positive 1/2 x minus 1 when I divide everything by negative 4. So go begin at negative 1. And we go up 1 over 2, up 1 over 2, up 1 over 2. Connect that line. And there it is, my point of intersection. 4, 1 is the point of intersection. We graphed it to verify our results that we got by the algebra.